Mehmet Şevket from Istanbul Technical University. These two friends are in Istanbul currently, they couldn't come. Actually, they are the real authors of this paper. We just had some design and simulations, so then we became a team. So our basic idea is not an ongoing project. That was an idea that we have in mind for some time. Then when we saw the competition, we just wanted to make it a little bit realistic and to show some ideas and share with you. So this is the first iteration of the space fan, so-called space fan. At the first iteration we plan to put the space fan on top of the panel, but as you can see it will cause to lose of the effective area for solar panels, which is not suitable in general. And we gave the basic dimensions here that it can also fit into ISIS launcher, for example, but not the NanoRex because it has 6.5, ISIS has 9.5 millimeters besides from the structure. And it was going to have a burning wire and resistors to burn the wire to open the system. Then we change and make the second iteration. In the second iteration, it's that you can see that you can use the solar panel area more effectively, and the opening system has been changed a little in order to increase the area of the drug. The lifetime didn't change so much, but you can have more power for 3 or even 1 new satellite. Because our main purpose was to keep using the satellite's internal volume for the subsystems. Even for our example projects, we barely fit inside 3U sometimes, so we didn't want to waste any volume inside of the satellite. So the system is basically under the panel itself, and here is the second burning wire to hold the rods. There will be an interface PCB, an opening control switch to give the ground station that at least the panels are open and the orbiting stage has begun. And there will be multiple strings inside of these places, and also to open the panels around the structure. And this is the calculated value for the burning the wire. Yeah, that was a bit too much. We gave 10 ohms. We gave 5 volts to a 10 ohm resistor for 30 seconds, which is less than 50 milliwatts, which I will mention again during the opening sequence. Before the opening sequence happens, the mechanism can be fed by a little solar cell because of its low power, and the mechanism will be redundant in a way that we will, here is a little microchip that it has a real-time clock, which will also have its little battery for real-time clocks. It will wait for a command from the OPC, but after the first, it will count the 1 year. After that 1 year, it will wait for command to OPC, do not open, and if anything happens and it couldn't get the message for 6 months, the system will open itself anyway with respect to power from the solar cells. And the third redundancy is that the system will be pre-calculated timing for the maximum time, for example 3 years, and then the system will open anyway if anything happens again. So as you can see, this is the stalled configuration, and first the panels open from the side. We only did it for the 2 sides to show its feasibility. And then there are 2 rods to hold the captain here. The first one opens, and because of the springs power, this one goes up and pulls the other one from inside. And this is the final configuration of a one panel. As you can see here is the one, and here is the complete opening satellite. As you can see, we don't have anything inside of the satellite so that you can use all the volume, and you can apply the same principle to 1U, 2U, or even half U. It depends on how long is your panel is. The folding mechanism is just like a hand fan that you put underneath your satellite. We considered a captain which is thickness is around 0.125 millimeters. So let's say that you fold it with a height of 1.8 millimeters, and you will eventually have 47 folding numbers. But this is these numbers are related to the errand of the circle, not the smaller part, because this will be the longer. So we made the calculations with respect to that, and when you fold it, it will be around 0.58 millimeters, which we have 1 millimeters here, and the rest will be from here. The captain will be attached here between these, and then will open in a sequence. Here are some basic properties that you can fit it under. These are for the 3U satellite, so basically if you shorten the rods, you can put it under 1U or 2U. And here is the thickness of the whole system, which I will mention one page later. We choose aluminium for the rods and for the springs. It makes for one panel only for 3U 12 grams for the rods, 10 grams for the springs, and nearly 8 grams for the resistor, captain, and the melting wire. So for, let's say you are opening 2 panels, and it will be around 60 grams, and I don't know if it will even cost this much, but we kind of wanted to include the cost of the opening of the solar panels, because you need to pay extra for them besides even if you build this. So yes, that I mentioned about the thickness of the panel and the mechanism underneath. So this is a basic, for example, structure from ISIS that you can use COTS components easily with this opening mechanism, and from one side of the other side it's 98.4 millimeters, and when you divide it into 2 you will have 0.8, and the thickness of our panel with the mechanism is 5.6, so when you include all of them you receive nearly 6.4. Sorry that this is for the, again, ISIS launcher. When you look at the CubeSat standards, it's 6.5 from our outer structure. So since this is from a little bit inside, you still have around 1 millimeter offset from the size of the launcher. This is the example of an ISIS launcher that you can see from structure to structure. It's 100, and the usable space is here around nearly 10 millimeters. That was the value for that, but it even fits for the 6.5 millimeters. And here are some cases that we use to make the analysis for the satellite. Okay, let me show. The first one here is used in these ones. If we use a 3-axis stabilization, the flight time is over 30 years, but if it makes a random movement when in that side, the flight time changes. This is what the SDK says. I don't have any hand calculations. So, and for this case, if you just open the panels itself, again 3-axis stabilization, your flight time will reduce to this. And then for the last case with these opening systems, your flight time changes with depending on 3-axis or passive aero stabilization. So you can, if you increase the size of the panel and open the other panels, you can have even less time. We wanted to mention that here, to make this simulation, we accepted some value which is on this paper. It says that it's possible to stabilize a satellite with about 15 degrees pointing error at each axis with passive aerodynamic stabilization. So we accepted that the satellite is wobbling in 15 degrees in all the 3 axes. So that based on that we received that value, and these are the regions for the aerodynamic stabilization, but we made the calculations depending on the preliminary design options that are told, which is 550 kilometers. So advantages of our system, it's so simple. You don't even have to waste any volume inside of the structure itself, and you can use it with the current code structures. It's cheap. You only buy some captain and rods and maybe a little bit epoxy, which is again not much for this. Disadvantages that we would like to mention is that the deployment mechanism has a spring. Also in the space vehicle mechanism, elements of successful design, it says that for every 55-degree change in the temperature, you will lose 2% of the modulus. So we are not sure about the spring material, but we wanted to mention it because we don't know, and if you have any idea about the material or the decay of the material, we would like to learn it. And also other disadvantage is that we don't exactly know how much the company will charge you for the opening deployable solar panels. So basically this is everything. Thank you for listening.
Thank you for your presentation. Okay, it's time for questions. I think we have enough time.
In your first or second slide, you said it's about 50 milliwatts of power needed to deploy. I'm not sure how you got to that number, because you said it's a 10 ohm resistor, 5 volts for 30 seconds.
300 seconds, 50 milliamps. That's right, two mistakes, 2 errors.
Yeah, it's just the watts is 25 divided by 10, so it's 2.5 watts for 30 seconds.
No.
It's 5 volts.
Okay.
Volt square divided by R, 10 ohm, that is 2.5 watts.
Sorry. Yeah,
So
that's milliwatt hour.
Milliwatt hour.
Yeah. So,
okay, so it's not
my
power.
mistake. Yes.
Okay, milliwatt
So
hour.
milliwatt hour. So that's why it's 50.
The other question is, you want to have your fan underneath the solar panel, a deployable solar panel.
Yes.
It was different in the abstract, but okay, so now it's underneath the panel. How much will the panel need to be raised so that your fan material will still fit underneath the panel? So you have to raise it by 5.6 millimeters?
No, this also includes the panel itself. A panel is around, for example, during our example projects in the lab, our thickest panel is 1.9 millimeters. So
with the cells?
Yeah, with the cells.
Panel and cells.
Yes,
okay.
yes. And beside that, let me grab here. Yeah, so this system itself is around, I took the PCB as 1.6 in this here, so 4 millimeters will be enough to push the panels aside, and we are not planning to put any additional stuff on the panels. For example, the antennas will be opening from the
Okay, have you folded your film material and did a test to see how thin can you fold the material like a fan?
Yeah.
How thin can you make it? Will it be able to fit in within that 4 millimeters gap that you have?
Yes,
Did you build a practical system, or was it just a paper design?
No. Let me show you. I don't know where you put it.
I don't see any photographs. I just see drawings.
So, if I consider the folding height of the maximum plate 1.8, when you fold it like that and when you push it in on top, we nearly get the same thing. We measured it with a micrometer. So I am folding not inside of this, but between these rods, and here it will be folded. So it fits there. The rods are also 2 millimeters in diameter, so we can fit this. And this is the thickest part of the folding. These parts will be much more small.
My questions are almost all the same as Stein, but
did you try this for? I mean the effect of the fold line is very important because if you fold some materials, maybe made of mylar or something,
The captain.
then the fold line has very big spring effects. So it is not easy to fold the small volume.
Yes. Yes. So that's why I showed this one. You do it one by one. You open it and then you push it.
But in that case, there are no fold line. The fan has some strict
Yes,
measures. But
yes.
if you fold the one film through the small, then there are many fold lines, and the spring effect is very not negligible, I think. So the thickness of the film is very thin, but the thickness of the fold line become very big, I think.
Yeah.
So
This is the thickness of the whole folding. This is the thickness of the film.
That's if you assume that the folds will be right on top of each other. You cannot be.
Yes. Yeah. Okay.
There's a curvature. That
yeah.
curvature cannot be zero.
Oh yeah. Yes. You're right. So yeah, that's why we gave 1 millimeter here. So that's right. There's a question.
Any other question? Okay. Yours is okay? Okay, so we have questions from the audience.
My question is, you are using 0.125 millimeter thickness captain.
Sorry?
You are using the 5 mil 0.125 millimeter thickness captain.
Yes.
As we know, there are different sizes, different thicknesses of captans. And what if the captan thickness is much thinner?
Much thinner. Actually, I choose the thickest one, and as I said, this is not an ongoing project. We just wanted to show some feasibility and simplicity of it. So I'm not sure of it, but here is the company that gives the details of the captain. So,
If it's 1 mil, that is 0.025 millimeter thick, would it work?
I don't know. Actually, I don't know.
So do you have any other question? Okay.
Hi, it's great to see all these different geometry concepts. I really like them. I'm from Nerex. Please visit the ICD to get the clearance right on the side of the pod, because the number I heard is not correct.
No, this is not your number.
No.
But
But
yours
you mentioned the clearance on the side. And
6.5.
yeah, it's more than yours.
Yeah. I also mentioned that.
Any other question? So if there is no question, let's thank our speaker again.